So now we are on to carboxylic acids, and in this little PowerPoint, we're going to learn about nomenclature, some properties, and some applications for carboxylic acids. So first of all, carboxylic acids, one of the last functional group that we're doing with oxygens in there, okay, and also that there is carbonyl with the with the functional group, and so that carbonyl is just like normal carbonyl you've seen before, so that's going to be there. And in addition to that, there is an OH, okay, on there. So together, COOH, that's what makes the carboxylic group. Now the R group here can be hydrogen also. It can be any number of carbons, but it can also be hydrogen. This OH, this has to be an H here, okay, for carboxylic acid to be an acid. So first of all, that there are going to be many carboxylic acid derivatives that we talk about. Carboxylic acid itself is a functional group, but there are many derivatives of that functional group, okay, which are the acyl chlorides, the anhydride, carboxylic ester, amide, and nitrile. And we will be doing all of this in the next part of carboxylic acids. In this one, I'm just going to focus on the acids, okay, not the derivatives of this, although we have to do all of this, okay, but right now we'll just focus on this. But I need you to know that there are so many derivatives, and what that really means with the derivatives is that you can convert one to the other for most part, okay. In carboxylic acid, you can convert to pretty much any of these derivatives, okay, so which means that when we do reactions of carboxylic acid, that's one of the things we'll be learning, okay, is to convert from carboxylic acid to any of these derivatives here. Now, all of these derivatives, if you can see here, which I think you can, is that they have a carbonyl group, okay? So I have the blue part on, just to color code it for you. The blue part is like the parent chain you can think of, okay? And then this is the derivative, which is the Cl, the pink one. And then here is the pink one, which is then making the anhydride. Here's the pink one that makes the ester. And if there's an NH2 instead of the OH, then it makes the amide. Now, nitrile is also a derivative of carboxylic acid, but it doesn't have a carbonyl, okay? So, but we do study it in carboxylic acids because from a nitrile, you can get other derivatives of carboxylic acids, and you can make it also from carboxylic acid derivatives. So we study it over here as well, okay? So that's all the derivatives that you need to know. The one that you're familiar with, the two derivatives that you learn about in functional groups, is going to be the ester and the amide, right? You do that in the beginning and you learn about these two derivatives, and that's because these two are the most stable ones, okay? And so you can find them in nature. So you study carboxylic acids, esters, and amides as derivatives. All the others you don't learn because they're very reactive and they don't exist in nature like that. Okay, so that's just a little bit about the carboxylic acid group. For the nomenclature part, you take away the E of the corresponding alkane and replace it with oic acid. Okay, so everything is ending in an acid, 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 so you kind of know that it's going to be an acid. We're also going to be using the common names a lot for carboxylic acids, and you remember what we talked about in the carbonyls before when we said that form is for one carbon and acid is for two carbons. Prop, as usual, is 3 carbons, but is for 4 carbons, right? So here also we have some general names, and we use general names all the time for carboxylic acids. So I've given you both of them. Again, the IUPAC is written first, and then the common name is given to you in italics. Okay, so the first one, the first carboxylic acid, is where the R group is hydrogen, so HCOH. That's called methanoic acid. So meth coming from the methane, or methane coming from the corresponding alkane, which is 1 carbon, and then acid, right? And then formic acid would be the general name for it because form is for 1 carbon. Then 2-carbon ethanoic acid, acetic acid, you probably heard of this one the most, most common acid that we deal with all the time. And then propanoic acid and propionic acid. Propionic is the common name. You have to kind of pay attention a little bit to propanoic acid and propionic because it's very easy to confuse as to which one is the IUPAC. Again, the IUPAC is going to be the one that sounds like an alkane. Okay, so propan is definitely sounding like an alkane. Okay, and that's the IUPAC. Okay, then butanoic acid and then butyric acid is going to be the common name for this. And that's where the common names end. After that, it's pentanoic acid, hexanoic acid, all very standard kind of names. Okay, so it's just the first four that have general names, and I can give you those general names also at any time. So definitely you should know them. I don't think they're that hard. And then, of course, you've heard about benzoic acid, right? We did that in aromatic systems. So benzoic acid is with the benzene ring and then the carboxylic acid. So more on nomenclature is if you have long chains, your numbering should always start from the carbonyl, okay, of the acid. So right here, that's where it should start because carboxylic acids are the highest priority of all the functional groups. No matter what you have, aldehyde, ketone, amide, whatever it is, okay, acids are going to take the highest priority for everything. So which means you have to number from there, and also you have to end in acid. Okay, so that's how you know that that's a priority group. So here you can see this is 5-methylhexanoic acid. Then here again, if you have an alcohol group, it doesn't matter. It doesn't take priority. You're just going to name it as a substituent, which is hydroxy. Okay, so this is 5-hydroxypentanoic acid. Here I've given you one with an alkene, so you just have to give the location of the functional groups, right? So 5-hydroxy or the ene part here, that's the alkene group. Okay, and so give those the location for the functional group that you have and then end with the acid. That's how it's going to be. If you have a cyclic compound with a carboxylic acid, then they're going to end that with carboxylic acid, just the way it is. Okay, so this one is 3-methyl cyclohexane carboxylic acid. That's what it's called. I usually don't give you too much nomenclature with cyclic compounds. I will just say if I need you to synthesize this, I will just say make this compound. That's all I would say. So, you know, but otherwise it's simple, right? Carboxylic acid can't get easier than that. So that's the nomenclature here. Then we can also have diacids in carboxylic acid, and then the diacids all have common names. You can also use IUPAC names, you know, like in this case where you have the 2 carbons, this would be ethanoic diacid. So you can do that too, but generally the common names are common for a reason, is because they are common, and that's how everybody knows these acids. If you don't know them, that's okay. Okay, don't worry about it. I just need you to know that there are a lot of diacids in this world, and we do deal with them a lot. So, you know, you should know that they are there. And so I've given you some of them. If there are more, you can always look them up, no problem. So some of the physical properties of carboxylic acids is one, of course, they have really high boiling points because they have hydrogen bonding, first of all, from the OH group. And then, of course, they have the carbonyl group, so they have dipole forces. So they have 2 of these very high intermolecular forces. Okay, so even something the most simplest of the acids, the first one, methanoic acid, also has a high boiling point. All right, and so as the molecular weight increases, boiling point increases. Diacids will have a higher boiling point than the monoacids. Of course, everything is doubled, right, in that one. So boiling point's really high, so you don't really have any gases. Everything starts from a liquid and then onwards to solids. Okay, solubility in water, smaller molecules are going to be soluble in water because of the hydrogen bonding. So you know, that's a pretty normal thing. Solubility decreases with molecular weight, which is also pretty normal. Remember, when we say solubility in water is yes, that generally means from carbons number 1 to 4. After that, you know, it could be more or less depending on what kind of functional groups you have. So here also for carbons 1 through 4, so up to butanoic acid is possible. Things are soluble, you know, maybe not completely with butanoic acid, but highly soluble. And then after that, it starts decreasing. Okay, so this properties start changing as you start increasing the number of carbons. And then the odor, oh yeah, okay, they smell. You can tell you have an acid because they're going to smell pungent. Pungent is a very sharp smell that you can get. I mean, if you want to get an idea of it, go and smell vinegar. That's the smell of acids, okay? And we're not talking about density because acids are soluble in water. So one of the things that we have to kind of review here is the acidity of carboxylic acids, because we have done this before, okay, that carboxylic acids are acids. Well, it says in their name, so they are acids. So first of all, what is the acidic proton? The acidic proton is the one that's going to be the H of the, that's attached to the oxygen. That's the polar bond. So that is the acidic proton, the most acidic proton, I should say. And so when you do an acid-base reaction, which you can absolutely do with any kind of a base, so this is the salt that you end up getting. Now, when you go from something like a carboxylic acid to the salt of that, you change the properties entirely, right? So here you have a carboxylic acid, which is a covalent compound. Now you have a salt, which is an ionic salt, okay? So which means you went from something that was covalent to something ionic. So which means what? You went from something that was low boiling point, low melting point, to something that is ionic, which has now electrostatic forces. So it has higher boiling points, higher melting points. This will be more soluble in water because it's ionic now, right? So you change the properties of the carboxylic acid, which is actually a big deal, by the way. Okay, when you can change the properties by just a simple reaction, that's a big deal. And we can use this in the lab to separate out the carboxylic acid if we wanted to by using a base, or even otherwise change the properties of a molecule by just treating it with a base, right? So you get something that is ionic, something, higher boiling point and whatnot. So, but anyhow, this is just because of the acid-base reaction, because of this acidic proton, okay, over here. So this is very traditional acid-base reaction. You can see this. So this is the acid, that's the base, you get the salt, and then you get the water also, okay, in the process. This reaction is in equilibrium because carboxylic acids are not that strong of an acid, okay, and that's the whole point of learning about this again, is that they are acids for sure, okay, but they're not super strong acids. They can be depending on what's attached on them, but we'll talk about that. But they are acids for sure. The products that you form, this salt that you form, this is called a carboxylate. Okay, so this is carboxylic acid and the product is called carboxylate. And when you're naming these kind of salts, then you would name them just like a salt, which means that cation first and then the anion. So cation first, so if there was a sodium here with the CH3COOH, CH3COOH is acetic acid or ethanoic acid. So here this would be either sodium ethanoate or sodium acetate. Okay, so as soon as you see the ate at the end, you know you're dealing with a salt. Okay, some sort of a salt. So if this is a sodium salt, it could be potassium, it doesn't matter. But the thing is, it's a salt because it's ending in ate, and then you don't change the name that much, right? So it was ethanoic acid to begin with. Now it's going to be ethanoate. So that's how you do the nomenclature, okay, for carboxylate salts. Here's another example with, if you had a propionic acid or propanoic acid, so that becomes propanoate. I would say that you can stick with IUPAC nomenclature if that helps you, like sodium acetate, acetate, and formate. Those are really, really common. But after that, if you want to just stick to IUPAC, that's fine, okay? Benzoic acid will give you benzoate. Okay, so if this is, we are reacting it with sodium hydroxide, you get a sodium salt, sodium benzoate. Okay, so keeping it simple. So the strength of the acids, okay, so carboxylic acids are actually fairly good acids, all right, and here you can see the pKs that I've given to you. So here you can see HCl, which is a fairly strong acid, is -7 pKa. So remember, the smaller the pKa, the stronger the acid. So acetic acid is 4.76. Phenol, not so acidic. It is acidic though, okay, we've talked about this before. And alcohols are also acidic, okay, maybe not strong acids, but they're acidic in nature. What does that really mean? It means you can treat them with a base. That's really what it means, and they will react with the base. So here you can see that acids are actually fairly good acids, okay, carboxylic acids. They are not as strong as mineral acids, but they're definitely strong, okay. So what we say here is how you can improve the strength of the acid is by increasing the inductive effect. Inductive effect meaning that if you add any kind of an electronegative group on the acid, then you can make this proton easier to go. Okay, because remember that's the acidic proton. So that's the acidic proton you want to dissociate, which creates the acidity. So the easier it is for this proton to go, the better the acid would be. Okay, so here if you look at all these acetic acids that I've given to you, different kinds of acids. So here if you had just the 3 hydrogens, normal acid, right? But if you add an OH, which is an electronegative group, then the acidity increases, okay? And if you have 3 fluorines on there, acidity increases even more, okay? Now it's almost as strong as, I mean, I wouldn't say HCl, but it's definitely getting there, okay? And this is trifluoroacetic acid, and trifluoroacetic acids are one of the very strong acids in organics. So if you in some cases don't want to use a mineral acid, you can easily use trifluoroacetic acid, which is also called TFA, for your reactions, because it's organic, so it will mix easily with organics, rather than having a mineral acid which needs water. Okay, so you can increase acidity, okay, by adding electronegative groups which cause inductive effect, okay, which is what? Which is pulling electrons towards itself. So this is what they do. They pull electrons and makes it easy for this hydrogen to go away. So here I've just given you the acidity for, different functional groups, but even if you were to compare something as simple as one group, okay, so something like Cl, and then maybe with fluorine, okay, over here. So again, same carbon, but with fluorine is going to be more electronegative. All right, on the other hand, if you had 2 fluorines, then that would be even more electronegative, right? And so therefore this is going to be the strongest acid of all. So that is how you work with inductive effect. Okay, so the closer they are, the better it would be. If it was far away, then not so much. Okay, so for example, if you're looking at fluorine like this and you were to compare 1, 2, 3, 4, then between 2 and 4, 2 is going to be stronger than 4, because in 4 the fluorine is farther away from the acidic proton. Okay, so that's kind of how you look at the strength of acids with electronegativity in there. Okay, which means you have electron withdrawing groups. Now you can have electron donating groups also, which will make it weaker acid, not stronger acid. So here is the one for benzoic acid derivative. So, just because you have a benzene ring doesn't mean it doesn't affect the acidity. It does. So as soon as you have the, some group like nitro group, which is an extremely electronegative group. So once it pulls electrons towards itself, pKa is, really low than others. Okay, so here is benzoic acid with just H there, 4.19. And then if you have electron donating groups like CH3 or OH, not so much, okay, of a strong acid. So more electronegativity will cause the pH to go lower, making it stronger acid. Some of the applications of carboxylic acids, first of all, acids are found everywhere. Literally, they are found everywhere. Okay, so vinegar, for example, it's a staple in all homes. One way or another, either as a cleaning agent or a preservative or as a souring agent, whatever it is, you can find vinegar and many uses of vinegar, okay, in anybody's home. So that's the most common one. A lot of fruit juices will also have organic acids, okay, and so it's extremely common. Formic acid is usually found in the sting of ants. So, when you think like, where would I find that? Well, that's where you find it. Butyric acid is found in spoiled butter, right? So butter, butyric acid kind of rings a bell. So that's what that is. Dirty socks will smell like hexanoic acid. Yeah, just because you wanted to know that, right? I know. You were curious, what is that smell? Hexanoic acid. Lactic acid is found in spoiled milk. Spoiled milk, remember, doesn't smell as good. You can tell by smelling the milk is bad, and that's the carboxylic acid smelling in there, okay? Amino acids are molecules that are inside our body, right? So we have 20 amino acids. which make up all the proteins in our body, which proteins would be the enzymes and the hormones and whatnot. So in the 20 amino acids that we have, the R group is different for all of them. And then you have the carboxylic acid and the amine group also, okay, in amino acids. So there are 20 of these molecules in our body, 10 essential, 10 non-essential. Non-essential meaning your body can make them. But anyhow, you don't have to know this. You will do this more in biochemistry where you learn all the 20 amino acids. But those are all carboxylic acids. So that's that for this little topic here. We'll go on to learn about the synthesis and reactions.